Hello and welcome to everybody for this our second day of Sustainable Composites, the Future. My name is Professor Steve Icorn. I'm from the University of Bristol in the Bristol Composites Institute. I'd like to make a special welcome to those people who are joining perhaps for the first time today for this session. The organisation of this event has been a collaborative effort between two University of Bristol institutes, the Bristol Composites Institute and the Cabot Institute for the Environment, and also with the National Composites Centre. We had expected to originally run this event in person. Obviously, COVID has taken over and we've decided to go ahead online rather than delaying, and we've been delighted in the response. We've got over 300 people registered to attend. We're not anticipating any technical problems, but this is the first time we've run an event like this, so please do bear with us. Now we have a 2-hour session today with several speakers, and we're looking forward to hearing from them shortly. There'll be an opportunity for asking questions following each speaker, and there's a panel Q&A session at the end of the session as well. Okay, so please use the Q&A function to ask questions. Now I will keep an eye on this, and I will ask questions on your behalf. There's no live questions. But please note also you can upvote questions that you particularly like to see being asked. And for those of you that are tweeting today, please note that we do have a hashtag here, Sustainable Composites 2020, and we'd like to remind everybody to use that particular function if they want to tweet the event. We do have speaker permissions to record the event, and we are also live streaming on YouTube. So recordings will be made available on the event page shortly after the session finishes. Okay, so without further ado, I'm going to now start by introducing our first speaker, and we're delighted to have with us Professor Mark Gillan. He's the Chief Technology Officer at Innovate UK. And he's going to talk to us a little bit more about the funding landscape for this particular area and within engineering also. So thank you, over to you.
Thank you very much. And if I can just share my screen. So hopefully everybody can, I'll just put it into present mode. So hopefully everybody can see my screen now. So as mentioned, my name is Mark Gillan. I'm Chief Technology Officer of Innovate UK, and I have been at Innovate for the last 6 months. Prior to that, I had quite a varied career, both in aerospace, in academia, but also in Formula One. So I've pinched the graphic in the top right-hand corner. I used to lead Formula One, our Williams actual racing team, and this is the topiary outside Sir Frank's facility in Grove. I think quite apt for today, looking at sort of sustainability and composites. We look at sort of the sort of F1 side. It's an area where I'm absolutely passionate about from a personal perspective, having been involved in both aerospace, automotive, and actually the 2 years prior to joining at Innovate in maritime and looking at commercial composite vessels, to look at what happens after sort of usage, and always thinking about sustainability with that in mind. And within so let me just push this forward. Within Innovate UK as a whole, one area that we have a potential issue with is awareness, and just people being aware of what is available from our sort of portfolio and our support. And one of the things I would always say is, at Innovate, as the UK's innovation agency, we are there not just to fund businesses, but also to help connect businesses and businesses and research collaborations across all the economic sectors, value chains, and all UK regions. So we work from the micro startups right through to the large companies, and really keen on fostering collaborations with the RTOs and universities. So in terms of what we do, I mean, this is a slide which is sort of typically used when we go out on our road shows. I think this highlights sort of our core funding over the last 13 years, showing 2.9 billion of core funding since 2007, and the gearing that it's had. But it really sort of undersells the activity, because if we look at the managed programs as well, then we have round about just over 9 billion of spend in those last 13 years. And in terms of projects, we've got sort of nearly 19,000 projects in operation, and that excludes even the sort of the fast start round that we held recently. The other area that just to mention, obviously it's not in this deck, but just to show you the sort of the dynamicism and where we live at the moment, we recently just yesterday announced a significant sustainability innovation fund of around about just 191 million pounds, split over a range of activities, and that's live at the moment, looking and open to businesses of all sizes, but really looking with the sustainability aspect. What I really want to do today is take you through our partner networks, particularly concentrating on the Catapult Network and what's available. So part of my role at Innovate as CTO is looking after our strategy and impact, so setting the future vision and direction for Innovate UK, but also I look after another directorate, which is our centres and networks governance, which includes the Catapult Network. And actually, again, there's awareness, I think, issue with a lot of our partner networks, and this diagram shows geographically the Catapult Network positioned across the UK, and we have 9 catapults, ranging everything from offshore renewables to medicine discovery, satellite applications, digital. I'll really concentrate today on the high value manufacturing catapult, which in itself is 7 separate centres. So those 7 separate centres stretch from AFRC in Strathclyde through to the National Composites Centre in Bristol, and form an extremely strong capability function in support of businesses of all sizes. And actually, prior to joining Innovate, I was a customer, both a customer and supplier into the HVMC, and I used to bring businesses of different sizes in. The last business I brought in was an ex-America's Cup company called Artemis, and you could almost see their eyes drop out of their head in terms of the capability that was sort of in the facility, and also the amazing resource in terms of technology and talent, which is incredibly important, and that talent acting as a magnet to draw in sort of other businesses and foster connections. So just looking at the sort of the Catapult and the composite capability, I'm just drawing and sort of delving in a bit deeper, looking at CPI, AFRC on its lightweight manufacturing, National Composites Centre, which I'll sort of focus on in a minute, particularly around the ICAP expansion, WMG in the automotive composites, and AMRC also in composite filament windings. You can see again a really nice geographical sort of mix, and also a very complementary capability. And I mean, there's a lot of numbers in these slides, and I'll not go into them in too much detail, but with the National Composites Centre, I think one of the key numbers that strikes me is 350 composite engineers. So in terms of knowledge base and capability, and particularly for the small companies, getting a foothold in and understanding and learning from other sectors, other companies, it's a really fantastic resource. And when you see in the sort of bottom right corner, nearly 50% of those organizations engaged are SMEs. I think it's, you know, that connection piece is key, rather than companies trying to reinvent the wheel, particularly when we're looking at the sustainability aspect and learning from others, and again through the different sectors. And I know, again, looking at the numbers on this graph, I've been involved and actually was chief executive of a renewable company, a wave energy company. But I've done a lot of work in offshore wind, and particularly even looking at floating offshore wind. And when you see, and you go up to say offshore renewable energy Catapult in Blyth, and you look at their test blade facility, which is taking a 100-meter span blade, it sort of puts it in perspective, the issues that we've got potentially being stored up, looking at sort of the sustainability issues that are being built up and what we have to deal with coming down the line. And when you think about 10,000 tons annually by 2035, it's not actually that hard to believe when you see the size of these blades that are being tested. And if you've never seen it, I strongly recommend looking up sort of the offshore renewable Catapult page and looking at the test facility for that 100-meter blade. And obviously they're growing and growing and growing. But that is obviously clearly an issue that we need to resolve. We need to get ahead of the curve, and absolutely, from Innovate's perspective, very key to pursue sort of innovative methods to deal with this. In terms of just running through a few programs, which I know will be discussed at more length through the course of the next few days, particularly pointing out on Rediscover program, looking to transform the UK's leading composite end of life, both the academia and commercial capabilities, into really interconnected supply chain, and looking at then the different sort of substreams, whether it be recycling, disassembly, and the circular material. So, sorry, bear with me. Sorry, I've had a bit of a moment. So I think it's absolutely key that, and obviously the reuse, it's absolutely key that we foster these activities and bring these to the fore. And sort of moving on just onto ICAP within NCC. Again, this is an area just to highlight the capability. This is a fantastic resource and investment, primarily funded through ATI and the LEP and through Catapult and with UKRI support, and looking at sort of 10 new tailor-made technologies done obviously and spec by NCC, 6 of which are installed. And I'd like to just concentrate on one. So on the bottom left, we have the sort of new braiding facility. And I worked for 2 years looking at and creating a strengthened places bid in Belfast with, say, Artemis. This is ex-America's Cup, who are world leaders in composite composite racing yachts, but looking at bringing it into the commercial world and looking at how to change their process into a more sustainable process, particularly for foils and other materials. So this is transformative in terms of capability and how to do something extremely complex in terms of shape and process in a timely manner, in a cost-effective manner, and ultimately a way that will be sustainable. This is just to give you a feel for the capability that is within the UK, which ultimately would be beyond the reach of companies and SMEs such as Artemis typically. And just in terms of sort of final, just giving you a feel for a couple of sort of typical sort of usage case studies. And throughout the UK landscape, we have numerous sort of funding activities ongoing, whether it be through ATI, APC, through UKRI as a whole, through Innovate UK, through some of the regional areas, even the European programs. And I understand that landscape can be extremely tricky to navigate. And the one thing I would say is there should be no wrong door. But I mean, utilizing the support either through the Catapult Network or through the Knowledge Transfer Network or through Innovate, coming in, asking where with your ideas and your concepts is the best area for support. Certainly you should never feel as if you've walked through the incorrect door. And that engagement piece is really important to us. And this just gives you a feel for just two quick sort of case studies, both similar sort of grant awards, 150K, both through the National Aerospace Technology Exploitation Programme, and both collaborative. One looking at sort of low cost fire, smoke and toxicity compliant composite components, looking at bioresins and obviously low toxicity recyclable solutions for future focus. I think it's a really interesting concept. And then the second one, which again is something which I've seen happen and evolve over a number of years, particularly is looking at biocomposites for aerospace interiors. And again, a collaborative venture through Coventive Composites. I mean, similar sort of level, looking particularly at obviously pre-preg composite materials for aerospace interiors, and trying to find novel solutions, alternative solutions to the petrochemical derived phenolics. But these are just examples of many which are in the pipeline at the moment. And certainly I would, if nothing else today, just try and raise the awareness of the amazing opportunities that are out there live, particularly if you're looking at our new Sustainability Innovation Fund that has literally just gone live yesterday. And please feel free to reach out, and certainly feel free to reach out to me in the future if you've got any questions in terms of potential funding and connections through our whole UK ecosystem in this particular area. Thank you.
Okay, thank you, Mark. Do you want to, that's it, put your video back on, that's great. Yeah, that's excellent. So thank you very much for that overview of what's going on in the UK. I think I'm just going to ask everybody if they've got any questions, please could you put them into the Q&A. Just ask any questions you want of Mark. Mark's ready now to take any of those questions. But perhaps I could start off and just sort of ask, can you see yet whether there's an upsurge at all in applications to Innovate UK in this area? Do you feel there's more of this coming forward yet, or is it too early to say?
So I think generally we're seeing a significant uplift in applications across the board. So to give you a feel, we recently did a 2-week fast start competition, and we had 8,500 applications, which is more applications than we had for the whole entire year across our whole programs. That aside, we are seeing, and we have a particular emphasis on around sustainability, net zero, and how we look to design in from the start the material choices to make sure that we're not sort of obviously storing up issues for future. So we are starting to see that, and we're thoroughly encouraging it. And you see that from our new fund, which has just been issued, which is both a sort of grant fund and an SBRI as well activity.
Yeah, and have you set targets against what investment you'd expect to see from UK companies in sustainability projects in composites going forward as a result of your investment? What sort of uplift would you expect to see?
So we're just in the process of putting together this 5-year strategy. Underneath that lies those through the sector areas, exactly that information. So it's being built up at this moment in time, and certainly something which I mean, very metric focused, and clearly if we want to understand success, one thing I would say is these are big problems, big issues that need to be tackled across, and it's not just in one particular area, it's across multiple sectors. So if we look at aerospace, automotive, energy, and I think actually the COVID-19 situation and the significant impact it's had into those sectors maybe buys us an opportunity to step back and look at how we can actually maybe leapfrog technologies and ideas. And maybe now is the time to take that leap and maybe take a leap against maybe the competition, but also to work together and tackle these ideas cross-sectoral. And that's something definitely that we're looking to try and help and encourage. And something we're even doing across the Catapult Network as a whole. So it's not just HPMC, but across our complete Catapult Network too.
Yeah, I'm getting a few more questions through now. So I've got a question here from Mike Campbell. Automotive focused projects currently active, focusing on either recycled materials or bio-based polymers that you're aware of?
Not off the top of my head, but I mean, I'll take them away. I mean, we have so many, and we have a lot of managed programs, and with the challenge funds, I'm sure we do. But with the specific questions, I'm very happy to get the experts in the area and provide that feedback on a one-to-one basis.
Yeah. There's a question here from Puta Sawata, who's asking, are there, again, it's probably a similar answer that you're going to give. Are there any focused research, is there any focused research developing bio-based resin polymers with enhanced properties?
And again, almost certainly yes. I'd be amazed if there were not. But again, with specific questions, I'm very happy to take them and follow up. I mean, I think one of the things is the breadth that we do. So we do everything from satellite application sort of pieces to agriculture. So there's a huge breadth, but it also means that there's a lot of activity ongoing, and actually sometimes those connections can be up. So I'm really keen to follow up any specific questions either in the chat or afterwards.
Okay, well we can keep a record of the questions and let you have those. There's a question here from Stella Job. There have been several competitions for circular plastics which are specific packaging, and the composite sector has not been in scope. Will there be any specific calls which cover sustainability of composites and other materials? So packaging is a focus, right?
Yeah. So that particular would even be in scope in currently what we have just opened yesterday. So I guess it comes down to the size of the actual program. But we constantly have a rolling change of actual managed or themed programs. But we're also moving, as you can see with what was just announced yesterday, to significant sort of open call and SBRI of what's available through the Sustainable Small Business Research Initiative, and as a phase 1, and then potentially looking at phase 2. But if you look on our Innovate website, the details of that Sustainability Innovation Fund are all there, and what's in scope and what's not.
Okay. Thank you, Mark, says Mariana Correa. Could you give us an overview of what kind of materials are being considered for seating applications in aerospace? There's a follow-up here. One of the most challenging aspects is finding a material that can be qualified in terms of flammability.
I think it brings on something that I didn't discuss, which again is a significant issue, is the regulatory aspects, and actually is a potential blocker in some of the growth aspects in some of the areas. So again, if you look at, say, marine composites for commercial vessels, actually regulatory wise, it's pretty prohibitive at the moment. Or there's maybe not that many regulations in place, which again is an issue. So one area that we're really keen to work with is the regulators, and that's been built into the strategy aspect. So in terms of specific material use, particularly if it's going to improve the sort of sustainability aspect. We're very keen to work with the regulators to try and, where possible, push those and fast track those through. So those are areas that we are keen on, and it's across sectors too. So it's not just, say, aviation or automotive, it's in the marine sector as well.
Okay. There's a question here, by Roderick J1. I don't know who that is, but Roderick J1, your question is being read out. Are there synergies with other research centres to join forces for a global problem as on the recyclability of composites?
Absolutely, and I think it's an area that we're starting to build up pace on. So I mentioned across Catapult Network, but I think it's wider than that. It's across all our research technology institutes, organizations, universities, businesses. Some of these programs and issues are obviously global and require significant effort. Clearly, we can't do everything on every topic, but I think we can definitely look at a few and from net zero through to sustainability, and actually try to drive those at pace with a concerted, connected, collaborative effort. And that's something which we have not necessarily been doing, but absolutely in focus at the moment. But still a little bit of work to be done.
So that was actually Jose Rodriguez. So he's just sent me a message saying what his real name was. Some people use a little handle for their questions. There's another very specific question here from Laith, asking what kind of bio-based materials are currently explored in the UK. So we'll perhaps send it to you out of this meeting, so you answer that specifically, or somebody from the conference may be able to answer it. There's a question here from Chris Eastland from Boeing, and he's asking, how do you measure sustainability from a life cycle standpoint? That's quite a technical question. I don't know if you want to take that one.
We could be here a while, and again, the whole life cycle analysis is key. So and also the life cycle analysis from a geographical perspective. So there's no point looking, say, with a UK focus if we are pushing it across the globe.
I think we could keep that question perhaps to the end.
Yeah, I mean, but it's a key question, and something which which is not going to get a 30-second answer, but it's not lost on us the importance of it.
Yeah. There's a question here from Fabrizio Scarpa. Thank you, Mark. Is there any plan to support the development of bio-based home-generated raw materials where possible? Most of the natural fibres used in composites are made elsewhere in the world, I guess. So what will grown elsewhere? So they're sourced from outside the UK, certainly. So is there any plan to support that?
Again, I'd have to take that back in and just check. I would always say that for any innovative idea, there's always an open call within Innovate UK, which is completely open in scope. Or on this particular area, for instance, again, it's open right now through the Innovation Fund. So I would strongly recommend having a look at our website. But in terms of what's happening at the moment, I'll take it away and come back to you. So again, I'll just have to collect all the information. I'll follow it up at the end.
Yeah, there's a question here actually from an SME, somebody from an SME, Dominic Hotwood from Bitres is asking, as a UK resin formulator with a portfolio of bio-based resins, the biggest challenge for SMEs is more often our visibility to the larger OEMs, users looking for collaborative partners for funded projects. Does Innovate have plans outside of KTN to develop ways to help promote the UK supply chain? So
we have obviously the knowledge transfer network, we have the EEN, which has got additional funding to help support businesses. In terms of the, again, one thing, if somebody comes to us with an ask, one of our issues is the awareness. First of all, knowing that we exist and knowing, say, that KTN exists. But once they know that we exist, coming to us with an ask, very, very happy to work with the business of all sizes to understand the needs and try and support. And I would always say, if for whatever we're a people business, so in terms of that connection and interaction, if for whatever reason you don't get an answer that you feel is what you're looking for, do seek additional help, or come. I mean, you've got my, have my details. Very happy to share them with the organisers, and please feel free to reach out, and I will make sure that you find the right people.
Thank you very much. Keep just saying to everybody online, if you keep your questions coming through, and Mark's going to stay around for the Q&A at the end. Don't forget also to vote for questions. If you've got any questions that you want pushing to the top, then make sure you vote for your own question. And I'll be asking the questions from the top, but I'll also try and move down to the bottom of the list as well and pick up questions as we go through. So thank you very much again, Mark. That was excellent, and
thank you very much.
Informative talk, and I hope to hear from you later on after the other speakers. So
thank you.
Now we're going to move on to our second speaker, and I'm very pleased to have with us from the University of Nottingham, Professor Steve Pickering. Steve has worked extensively on fibre recovery, particularly carbon fibre recovery, and he's going to talk to us about the challenges of fibre recovery from thermoset composite materials. So over to you, Steve.
Thank you very much, Steve, and I'm just sharing my screen now. So I hope that's I hope you can see that, and I'll just go into presentation mode now. Right, so I hope you can all see my screen there. So yes, I'm Steve Pickering. I'm Professor of Mechanical Engineering from the University of Nottingham, and what I'm going to talk about today is some of the challenges of recycling thermoset composite materials. Particularly, I'll focus on carbon fibre and how we can get the most out of the fibres that we recover and what we can do with them. So the presentation content, first of all, I'll just focus initially on the composite waste streams I want to consider. Then I'll talk about fibre recovery technologies for thermoset composites. And the second half of the talk, I want to focus on the issues and opportunities for the reuse of recovered fibre as a reinforcement, using it as a reinforcement material, and suggest what we need to do to get the highest value out of the material. So as one of the slides that Mark showed us earlier in the last presentation, there's a lot of composite waste around, both in the UK and in the world. Most of it is actually glass fibre. As in Mark's slide, he showed that over 90% of the composites waste is based on glass fibre. But most work on recycling and recovery has been done on carbon fibre, because that's where there's much higher value in carbon fibre. So the different forms of waste, there's dry fibre waste, where this will be from weaving or preforming and pre-preg manufacturing operations. I'm not going to discuss that really. I'm going to focus more on the composite materials. So this could be waste pre-preg or moulding compounds from manufacturing operations, which you could then cure before you recover the waste. But of course, there's a lot of cured thermoset composite waste from manufacturing operations. Particularly with carbon fibre, that's probably where the bulk of the waste is, the cured waste is at the moment. But of course, all the materials that are being manufactured there, and when it comes to the end of life, the waste needs recycling then. So I'm going to be focusing really on cured composite composite waste where we're using thermoset polymers. Of course, some composites are made using thermoplastic polymers, and there are other issues in terms of recycling those materials that you wouldn't necessarily want to separate the fibers from the polymer. You could remold them, as you can do with thermoplastics, and I'm not going to focus on that. So the focus of this talk is going to be about thermoset composites. Now, I'm going to review the fiber recovery processes, and most of the processes use heat to break down the resin and allow the fibers to be separated. But with all the processes, there's some preparation of the waste needed before it goes into a process, so that inevitably means some size reduction. There's the actual process itself, and then there will be some post-treatment operations, which again may involve further size reduction to get the fibers in the form you want to reuse them, some packaging operations then. There is some commercial operation already taking place for carbon fiber recovery, but there are a lot of processes under development, and a few of them are yet commercialized. So let's have a look at some of the recycling processes. I'm going to focus on initially on carbon fiber, but I will mention glass fiber as well. So pyrolysis, a pyrolysis process, basically the idea here is to heat the composite material in the absence of air. The polymer resins will break down and break down by the action of the heat, and leave the fibers behind. Now, the problem when you break down polymers in the absence of air is that you tend to form a pyrolytic char. A char is left behind on the fibers, and this means you can't separate the fibers, and they're difficult to reuse. So you need to have a controlled atmosphere where you can offer a little bit of oxygen to oxidize this char and giving clean fibers. So there's probably more work being done on pyrolysis processes than any other, and there are already a number of carbon fiber recovery operations in the world using pyrolysis technology. And one of the most notable of those is ELG carbon fiber, which is here in the UK. And you'll note from the program of the workshops this week that Fraser Barnes from ELG will be giving a presentation tomorrow. The key issues in pyrolysis processes are being able to remove the pyrolytic char and ensure quality of the recovered carbon fibers, the individual filaments, and also to think about how you're going to control the length of the carbon fibers. You're going to do it by shredding the material before pyrolysis, or have some chopping processes after pyrolysis. So that's pyrolysis processes. Second process I want to mention here is a fluidized bed process. This is one we've developed at the University of Nottingham. The idea is here that you would have a fluidized bed, which is a bed of sand through which you'd blow air, heated air, and you end up with sort of looks a bit like a bubbling liquid. And into that material you could feed waste composite material. It will be air used as the fluidizing medium in this process, and that in that process, working at typically temperatures about 550 degrees C, the polymer would be effectively broken down and oxidized, leaving behind the individual carbon fibers, which would then be carried out in the airstream from the bed, and can be separated out to give clean fiber waste here, and the gas stream can then go on for further oxidation and heat recovery, and you use the recovered heat to recirculate round again, and with the air going through the fluidized bed. So you can recover very clean carbon fibers. You get energy recovery from the polymer, and as well as being a fiber recovery process, it's effectively an air classification process. So it's able to separate out different contamination from the material as well. So if there's any metallic parts in with the waste, then that stays behind in the fluidized bed. So it's very good, and also if there's any other contamination that is oxidized in the process. So it's very good for end-of-life waste, and it's a robust process. Some of the key issues: it requires a source of hot air, so there's a need for a heat recovery system. And also, if you've got a mixed waste with some contaminants, you need to recover those from the fluidized bed after at the end of the process. But there is technology for doing that. The next process I'd like to mention is microwave pyrolysis. This is a variation on the pyrolysis process. Again, you're heating in the absence of air, but the heat source this time comes from microwave radiation, and particularly applicable for carbon fiber composites, because the microwaves will absorb the carbon fibers absorb the microwave radiation, and so effectively the material is heated up from the inside. And it's been found that there's no pyrolytic char formed on the fibers when you heat with a microwave process, and so it has that advantage. And similarly, because you're in the absence of air, there's no fiber oxidation damage at all. There's no oxygen there at all, so no, you're not going to get any oxidation damage. But you'd need to shred the materials fairly uniformly and have dispersed fragments going through the process for the microwave process to work properly. And I think the difficult issues in microwave pyrolysis are really the difficulty in controlling the energy input to ensure full polymer removal. Unlike other pyrolysis processes where you control the temperature, in a microwave process you control the energy input, and so it's difficult to control the process temperature, and you need and so there are some quite difficult control issues with this form of pyrolysis, and it's only been developed at the laboratory scale so far. All the processes I've talked about so far really only recover the fibers, and there's the polymer gets degraded. So it would be nice to have a process where you could recover the polymer as some chemical products from the polymer as well as the fibers. In most carbon fiber composites, the carbon fiber itself, it's over 2/3 of the weight of the material is carbon fiber. So the polymer is a small fraction of the total, but nevertheless, it's a valuable material to be recovered. So a number of processes have been developed, which are broadly called solvolysis. These involve effectively dissolving out the polymer at high temperature conditions. So this would involve heating in the presence of a fluid to break down and extract the polymer. Some of the fluids, a number of different fluids are being considered. Some very strong acids, but they're not very environmentally friendly. But supercritical fluids such as propanol or water, which are more environmentally friendly fluids, have been considered, but these do need quite high pressures to operate at. You can obtain very clean, very high-grade fibers from these with the solvolysis process, and you can recover some useful chemical products. Although you don't really, with cross-linked thermosetting resins, they usually don't break down in such a way that you end up with a usable mono, but you do end up with a feedstock that could go back into a chemical process. Generally, the temperatures, you'd start the process off at fairly high temperatures, and you thermally degrade the polymers to begin with before the supercritical fluids or other fluids would dissolve out the polymer. But there are some lower temperature catalytic processes that have been proposed, and Adherent Technologies in the USA are one company that have proposed that. I think the key issues here is that particularly if you're using supercritical fluids, that needs very high temperatures and pressures, and particularly high pressures means expensive equipment, and so there's a capital cost challenge there. Just wanted to say a few words about the way in which these thermal recycling processes work, particularly the fluidized bed and the pyrolysis processes. You'd start off with a composite feed and you'd heat it, and the polymer degrades and leaves behind a pyrolytic char as well as the fibers. So you can see here we've got the fibers embedded in some resin. Here are the fibers. After initial pyrolysis, there's still some char holding the fibers together. And so to get rid of the to produce recover good clean fibers, you'd need to apply some air to give some oxygen to oxidize the char. And in a pure pyrolysis process where you might have a stationary bed, the air comes in from the outside, initially oxidize the char on the outside of the fragments. But to clean the fiber, remove the char in the middle, you've got to allow enough time for that to take place, and you don't want to overcook the fibers on the outside in a process like that. But this is where the fluidized bed process has an advantage, because the fibers, once the fibers have been released on the outside here, they're removed within the fluidized bed and elutriated, as we say, and so effectively the fibers get removed from the process as soon as the char has been reduced, and so you don't overcook the fibers, and you don't need to worry about thick sections of material. So the key question is, what are the properties of these recycled or recovered fibers? Well, generally, it's been found in all these processes that you have good mechanical properties. The modulus of the stiffness of the fibers, the modulus is largely unchanged in all these processes. There is some loss of strength, and particularly in the pyrolysis and fluidized bed processes where there is some oxygen there to produce the clean fibers. But nevertheless, this can be controlled, and they're not strength loss may be typically 10% or so. And you can produce good clean fibers, as I've shown here, but it's in a fluffy form. There's quite good surface chemistry. Quite a lot of publications have shown that there are good functional groups still left on the surface of these fibers that provide good bonding to epoxy resins. So you don't necessarily need to resize the fibers. The sizing that was originally on the fibers has been degraded as well, along with the polymer, but nevertheless, you don't necessarily need to resize them, because they will bond well to epoxy resins, as shown just here. We're producing clean fibers, but the physical form, these are filamentized discontinuous fibers in a fluffy form, and here's a typical picture of the sort of fiber you produce, and they will have a length distribution. They'll not be with all of one length, and that's unlike any commercial grade of virgin fiber. And so there's a need to think how those can be reused to get the best out of the recovered carbon fiber. So this is one of the key challenges. It's not just in recovering the fiber, but think how we can reuse it. I'll just say a quick word about glass fiber composites, because there are very large quantities of these materials, large quantities of end-of-life thermoset composite waste needs recycling from the wind turbine, marine and construction industries. There's a way of disposing of these materials in cement kilns, and that technique has been already established in Europe. We don't yet do it in the UK, and in the cement kiln process, the polymer provides the energy, and also the glass and the fillers can usefully contribute to the minerals in a cement. Mechanical recycling can be considered, where you would just shred the materials up, and you don't necessarily separate out the polymer from the fibers. If you have if you mill into a very fine powder, you can effectively produce a filler, or if you shred less finely, you can have some reinforcement materials, as you can probably see from this picture here. The problem in reusing these materials back in new composites is that the alternative materials, the virgin fibers and virgin fillers, are very cheap, and so it's difficult to make this work economically. You can also use thermal fiber recovery processes, and we have shown that the fluidized bed process can also recover clean glass fibers. There's quite a lot of strength reduction at high temperatures. You can see from the slide here. When you're processing at 550 degrees C, you might only have, you might get the same modulus stiffness of the fibers, but there'd be a substantially reduced tensile strength. But there is technology that's been developed in the last few years to recover the strength of these fibers, and so there's a potential for having thermal recovery processes. But I think the main problem with glass fiber is the very low cost of alternative virgin materials. Glass is much cheaper than carbon, and many of the polymers are cheap too. So that's the challenge. So let's think about how we might reuse these fibers. And in this So if we've got some discontinuous recovered fibers, carbon fibers, let's look for how might we reuse those? Well, if we take those fibers in the random form they've been recovered, I've shown a number of applications at the bottom here, going from low fiber volume fraction on the left to a high fiber volume fraction on the right. So these are where you're using the fiber as a structural reinforcement in new polymer composites. You could put these random fibers directly into a bulk molding compound, and that would be an easy thing to do, but you'd only get very low fiber volume fractions, 10 to 15%, and these aren't very these are not really very high grade in their properties. You could turn the material into a non-woven mat by using paper waking type processes to produce a non-woven, and you could use compression molding to produce intermediate volume fraction, say 10 to 30%. So again, the higher value materials here. But carbon fibers are usually used in very high fiber volume fraction applications where they get up to 60% fiber volume fraction, and it's difficult to achieve that with random processes, as I'll explain in a few minutes. So if you want to get to the high fiber volume fractions, you really need to align the fibers in some way so you can pack them together. And there are a number of processing techniques which might be considered here, and I'm going to focus on a wet processing technique in a few minutes. Now, this graph really shows where what distinguishes carbon fiber as a structural material. This graph shows specific modulus or stiffness of the materials on the y-axis, and specific strength or strength divided by density on the x-axis. And lots of different materials are shown on here. Metals, aluminium, and steel are shown just are around here. Some of the glass reinforced composites are down here, but carbon fiber composites are up here on the top of on the top right, and they're well away from other materials. So, and you can achieve these sorts of properties, these specific strength and stiffness, by using a very high fiber volume fraction, 60%. And when you're using carbon fiber at these volume fractions, then the carbon fiber materials don't compete with any others, and you're really getting the most value out of the material. So how can you achieve high fiber volume fractions? Well, you can't do it with random fiber orientations, and we've done some work with making random non-woven mats using a paper making technique to make some composites. And this graph here shows the mechanical properties, the stiffness and the strength on the y-axis, different fiber volume fractions on the x-axis. And as we increase the molding pressure to give to squash the fibers together and give high fiber volume fraction, and the best properties that were achieved at around about 30% fiber volume fraction. But when we applied more pressure, it just broke the fibers, and we didn't get the strength decreased, and the stiffness was not what we were expecting. So
we've got 1 minute to go. Yeah.
Okay. Thanks very much, Steve. So I'll move on to this slide. So what we need to do is to look at processes for being able to align the fibers, and we've developed a process at Nottingham based on some technology developed a while ago by the MOD, which is to take a suspension of fibers, pass them through a convergent nozzle, and to align them, and then deposit them on a mesh inside a rotating drum. And here's an image of the jet. The fibers are in there, and we're depositing them on the drum. And we can achieve with this process, we can get some very high degrees of alignment, and at autoclave molding pressures, we're able to achieve fiber volume fractions of 46%, and with 3mm fibers, making some 2mm thick laminates, we were able to achieve high modulus here of around about 100 gigapascals, not about over 90% of that of what you'd expect from perfectly aligned from virgin fibers, and you can see a cross sectional here, and all the fibers are packed together fairly well and all fairly well aligned. So this is an opportunity. So to get the highest the highest mechanical properties, you need to have processes to align the fibers. And we were getting up here towards the composites we'd made here. We're getting up towards those from virgin fiber, and they were well away from the competing materials. So you're getting some of the best out of the recovered fibers by aligning them at high fiber volume fraction. So to summarize then, a range of carbon fiber recovery processes are proposed and commercial exploitation is developing. Recovered carbon fiber can be processed into non-woven fabrics, but to get the highest value out of these materials, so you can get the most out of the carbon fiber, your recycled carbon fiber, you need to have alignment processes, and there are some under development at the moment that show promise for being able to get the most out of the recovered carbon fibers. And finally, just to say that glass fiber composites recycling still remains a challenge, particularly because glass fiber is much cheaper than carbon fiber. But nevertheless, carbon fibers being a more expensive material, that's sort of paving the way at the moment in recovery technologies. So thank you very much indeed.
Thank you, Steve. If you just want to unshare your screen now.
Sharing my screen now, there we go.
Yeah, okay, excellent. Well, thank you very much. Very interesting talk. We've got a couple of questions on here. You ready to take questions?
Yes, I'm very happy to take questions.
I don't know if you'll be able to answer this one specifically from your talk, but it looks like it did relate to your talk. It's from Patrick. Are there any unique challenges when addressing hybrid reinforcement materials in a composite, such as glass carbon, protrusional glass carbon infused fabrics?
Yes, I think there's a very big challenge in dealing with hybrid composites where you've got glass and carbon together, because because separating glass fiber and carbon fibers is not is quite a difficult problem. In fact, we've got a research project at the moment where we're having a look at that, but it's quite challenging to think if you've got a hybrid composite how you would separate out the carbon and the glass. And so that's a current research area. Yes.
Yeah. A question here from Sean Elgie. Are you aware of any non-trivial applications or uses for mechanically recycling composites, or mechanical recycled composites?
So yes, so if you were to mechanically recycle, so this mechanical recycling is where you don't separate the polymer from the fiber, you just co-minute the material, shred the material up. Some work has been done on that. I mean, with glass fiber, there's been quite a lot of work done over the past 20 or 30 years looking at mechanically recycling these materials and say getting some the fibrous fractions and recovering them back, putting them back into composites. One or two, but they've never been found to be commercially viable. One or two manufacturers can actually put their own waste back and find that it's, as long as that, because they know what the material is, that can be recovered back again. But it's not an easy, it doesn't look particularly attractive economically. With carbon fiber, there's been a bit of work done looking at, say, shredding carbon fiber waste and say perhaps putting it back into reinforced asphalt or reinforcing concrete and use it. And that's a potential. Those are potential applications that you could use it for. But you don't get really the same reinforcement value you would get because you've still got the polymer there. You don't get the same reinforcement value you would if you were to separate out the fibers from the polymer. And so that's where most of the research has been done.
Okay, well, thank you very much. So we'll now move on to our next speaker. We have Dr. Soraya Pimenta from Imperial College. Soraya is going to talk to us about discontinuous composites, a route for manufacturability, damage tolerance, and sustainability. So over to you, Soraya.
Thank you very much for the introduction, Steve. Good afternoon, everyone. I am Soraya Pimenta. I am a senior lecturer at Imperial College London, and I will be talking to you about a particular type of composites, so discontinuous composites, and how they can help us overcome what are arguably the three main challenges for composites. So manufacturability, damage tolerance, and sustainability. So we all know that carbon fiber composites, they have outstanding mechanical properties, so outstanding specific stiffness, outstanding specific strength. And this means that these materials are usually used in a very high performance structures, such as aircraft and racing cars. Now, these outstanding properties come on the one hand from the type of fibers that we use in these composites. So carbon fibers are perhaps the stiffest and strongest engineering material that we have available. They also come from the fact that we tend to use very high performance matrices to make these composites. But a lot of the value of the composites and part of their outstanding properties really come from the fact that we have the fibers structured in a very well-defined architecture inside the composite. So as you can see here on this image on the right-hand side, so the fibers, they tend to be continuous and they are very well structured, so very well organized inside our composites. Now, this continuous and very well structured nature of the fibers inside composites, it raises several challenges. So the first one is manufacturability. The fact that the fibers are continuous and the fact that we want to keep them in a structured architecture means that it becomes very difficult to conform these composites to complex 3D shapes. And it also means that we need to use rather slow and expensive manufacturing processes, and I will give more details about this later on. The second challenge that we face is damage tolerance. So the structured and continuous architecture of the fibers, it creates weak paths that basically can trigger and propagate failure. And any geometric discontinuity that we have in our structure, for instance, any hole, becomes a weak point to trigger failure in the structure because it breaks the continuity of the fibers. And a third challenge is sustainability. So you have heard Steve Pickering's talk on recycling of composites and how that is so difficult to achieve. So you have seen that the process of recovering the fibers is on its own difficult, but then a main challenge that we have is the fact that the form of the recycled fibers is discontinuous and completely different from anything that we can see with virgin carbon fibers. So these three challenges actually create the outline for my talk. So I will go through each of them, explain in more detail what are the challenges posed by continuous fiber composites regarding each of these three aspects. And then I will show you how using discontinuous composites can be a way to overcome these challenges. So if we start by thinking about manufacturability, so here I'm showing on the left-hand side a breakdown in terms of costs and in terms of manufacturing time of composites versus aluminium and steel. And so if we look first at the cost, we can see that it's much more costly to make a structure out of composites than it is out of aluminium and steel. What might be surprising is the fact that most of that cost comes not from the material itself, so not from the cost of the fibers or the cost of the matrix, but actually from the manufacturing process. So the cost of making, of going from those fibers and that matrix into an actual component. And that is mostly due to the fact that you can see on the bottom that manufacturing processes for conventional composites, they take much longer than those for conventional metals. And the fact that we have such expensive and so slow manufacturing processes are really a consequence of the continuous and the well-structured architecture of the fibers inside these composites. So if we look into this in more detail, so we have a first problem, which is the fact that to manufacture continuous fiber composites, we usually rely on processes that require a lot of manual labor. And this is because we want to control very precisely how these fibers are placed inside our structure. Now, it's possible to automate some of these processes, but even if we do that, making components out of conventional composites is intrinsically a layer by layer process. So the conventional form in which the fibers and the matrix can be bought are basically thin sheets. Those sheets can be usually down to 1/8 of a millimeter, meaning that if you want to make a plate 3 millimeters thick, which is a normal thickness for a thin structure, you actually need to lay up 24 layers of these composites, and that obviously takes time. Now, there is also the fact that we want to preserve the architecture of the fibers, and that again it means that we need to place those fibers and those materials exactly where we want them. And altogether, this makes it very difficult to make 3D shapes with complex geometries. A third problem that we have is the fact that after placing our intermediate materials and the fibers exactly in the positions that we want them to be, we still have to cure the matrix. So we need to basically bake the matrix, which can be done under heat and pressure in a massive oven, as you can see here, and that process typically takes a few hours. So what we can do using discontinuous composites is, instead of using this conventional process that you can see here on the left-hand side in summary, is to use multi-scale discontinuous composites with fast curing matrices. So basically the type of materials that I'm talking about has a microstructure that you can see on the top. So at the smallest scale, you have several thousands of fibers very well packed and aligned in the same direction. These make toes, as we can see on the image in the middle, and these toes themselves are discontinuous and randomly oriented inside our structure. Now, the fact that we have these two scales means that on the one side, we can pack the fibers very efficiently inside the composites, and on the other side, we have a discontinuous and randomly oriented structure, meaning that we can just take a charge of the material, put it inside a mold, apply heat and pressure, typically with short cycles because we are using fast curing matrices, and off we have our 3D component in a much faster and much cheaper way compared to if we were following a conventional process as highlighted on the left-hand side. Now, these materials, they have significant advantages. So the manufacturing time can go down to 2 minutes. The total cost of making a component can go down to 25% of that of conventional composites. These materials are still quite lightweight and very high performance. So some of the properties, they actually match those of conventional continuous fiber composites. And we are able to make components with very complex geometries, and we can place the reinforcement exactly where we want it to be. So all of these advantages have led this type of materials to be used in a wide range of applications, so ranging from automotive to aircraft and to sports. But we still have some challenges, and one of the challenges comes directly from the advantages in terms of manufacturability. So if you think about what happens when you manufacture a T-joint, as I showed in the previous slides. So we have a charge, and the beauty of these materials is that they can be processed by compression molding. So you can just apply heat and pressure, and the material will flow and fill whatever mold cavity you have. Now, what this means is that the fibers will align themselves in the direction of the flow. And this means that we are going to have properties that are going to be different from one point to another. So here on the right-hand side, you can see that we can predict this effect of orientation of the fibers in the direction of the flow by simulating the manufacturing process itself. Now you can see here that I have highlighted points in red, blue, and green. And because these points have locally different orientations of the fibers, they are going to have locally very different properties. We have quantified this effect, so that can basically be done by making a plate where you control the amount of flow that you have, and then selecting the material from where you test your mechanical properties according to that flow. And you can see here on the right-hand side that indeed we do get properties that are significantly affected by the flow. And what that means is that at each point of your structure, you are going to have different properties of the material. So effectively a different material from a design point of view, that you need to take into account when you are designing your parts. So our contribution at Imperial to do this has been to develop models that, based on the results from simulations on of the manufacturing process, allow you to predict exactly what are going to be the properties that you are going to have at each point of your structure. Now, I will not go into the details of those models, so you can check those details here if you would like. But basically, what we are able to do is to replicate the results affected by flow that we see experimentally. So the experimental results are shown on the darker color, and the modeling results are shown on the lighter color. So moving now from manufacturability into damage tolerance. One problem that we have with conventional composites is the fact that they are very sensitive to notches. So as I mentioned previously, as soon as you put a hole in the conventional composite, you are basically breaking the continuity of the fibers, and that means that you create a very weak spot locally. And this becomes very problematic when you think about real life structures. So on the left-hand side, I'm showing the fuselage of an aircraft, and you can see that basically the structure is full of notches. So when we do notched tests, so with a geometry that you can see here on the top, with the discontinuous composites that I mentioned in the previous section, so sometimes we do see that failure happens near the notch, as we would expect with conventional composites, but other times we actually get failure away from the notches. So basically the material seems to be insensitive to the presence of notches. And if you think about the notched strength, you can see that the strength of these materials is much less affected by the presence of notches compared to a deep reduction of notched strength for conventional composites. So this is, of course, very good news. So we can say that these materials are the ultimate notch insensitive material. But this basically happens because the properties of these materials are different from one point to another. That difference is in part controlled by flow, as I mentioned in the previous section, but it's also controlled by a stochastic process. So it's controlled by chance as well. So if you make two specimens nominally in an identical way, one of them will behave in a certain way, the other will behave in another, and there is no way for you to be able to know what you get until you actually the specimens. And this, of course, brings a question about how these materials in complex structures as the one that you can see here. So if you want to use these materials in a car, how can you design the car so that it's still lightweight and makes full use of the properties of composites, but is safe within this material variability that we actually have. So what I'm going to show you, just a case study for an actual components of this car. So we are focusing on the lid of the engine of one of the last Lamborghini's cars. So on the left-hand side, you can see a geometric model of the structure. So in terms of size, this is longer than 1 meter. You can see that it's a real structure, so it's connected to the rest of the car in a complex way. It has multiple materials, and the part made of composite is the one that is shown here in red. So what we do in the framework that we have developed is to, according to process simulations, assign stochastic properties to the composite. So each model that we run will have different properties from the previous model. And basically that allows us to quantify the reliability of these structures. So on the right-hand side, you can see that instead of predicting that this structure will fail for sure at one spot, you can see that we identify 10 spots where failure can initiate. We can quantify how much more likely it is for it to fail from one point rather than from another. And we can actually quantify worst case scenarios of how close the failure load is from the load that we are applying to the structure. Again, I'm not going to go into the details of how we have developed this framework, but we have used it for a case study with real life structures, as you have seen, and we have also validated against this type of simpler tests that we have run in the lab. So moving now to the final section of this talk. So this is related to sustainability. You have seen from Steve Pickering's presentation that composites are now used in a wide range of applications, so some of them very large scale. And this creates a problem in terms of recyclability. So you can see that compared to, again, aluminium and steel, we are still not recycling the vast majority of the composites. And Steve Pickering has explained brilliantly why this is so difficult to achieve. Of course, that with the increasing use that we have in carbon fiber composites, together with the economics of the process and also some incentives from legislation, it becomes more and more important to recycle. And as Steve already mentioned, basically the process process that we use is that we remove the matrix from the composite, recover the fibers, reimpregnate the fibers with a new matrix, and create a new component in a loop that can continue. Now, by doing this, it's possible to make recycled composites which are discontinuous, which are randomly oriented, and as Steve mentioned, which compete with other structural materials such as aluminium and glass fiber composites, both in terms of stiffness and strength. So the fibers can be recycled through pyrolysis. Again, Steve already gave an overview of the process. I also think that there will be a presentation tomorrow from this company with more detail about the pyrolysis process itself. But basically, I just wanted to highlight that if your pyrolysis process is too aggressive, then you get damage on the fibers. If your pyrolysis process is too gentle, then you get some residual resin still holding the fibers together in bundles. And if you get your pyrolysis process just right, you get clean fibers with pretty much very similar properties as the ones that you have for the virgin composites. Now, these residual bundles that you can see here on the right-hand side, held together by residual matrix, they can be seen as a defect, but they are not necessarily so. So when we then reimpregnate the recycled fibers with a new matrix to manufacture a composite, we can very often see this type of microstructure where you have dispersed filamentized fibers that are very clean after the pyrolysis process, but also some fiber bundles that are held by that residual matrix. Now, when you have a crack propagating in these materials and that crack meets a fiber bundle, basically what a crack needs to do is to go around the bundle because it does not have enough energy to cross it. These bundles, they also mean that locally you can increase the fiber volume fraction of carbon fibers inside your composite, which also contributes to improve stiffness and potentially strength. So basically the opportunity that we have here with recycled composites is that if we make use of these fiber bundles, we can not only recover fibers with better properties because we are less likely to damage them during the pyrolysis process, but we are also able to get recycled materials which are twice as tough as aluminium. And that brings a possibility of creating damage tolerant applications in a wide range of industries. So this has concluded the main part of my talk, so I'll just go quickly to the conclusions. So you can see here an overview of the opportunities, the challenges, and the way forward that discontinuous fiber composites offer. But I'll just like to finish with a thought. So these materials, they are suitable for large volume industries, for instance, automotive. So if we think about replacing half of the structural weight of a car currently manufactured with steel with discontinuous carbon fiber composites, we could potentially altogether save up to 30 billion pounds per year on fuel and 60 million tons of CO2 emissions per year. So this is really, I believe, a good opportunity that we should try to capitalize on. So just before finishing, I'd like to acknowledge several members of my research group, other colleagues and collaborators, and also funding that has contributed to this work. And I'll be glad to take any questions you might have. Thank you.
Thank you very much, Soraya. That was excellent. And we have a number of questions that we're probably going to save till the end, but because it's probably more general to get the more general questions. But I have a few specific questions that I'm going to ask you. have there been any work on the flow properties for faster manufacturing processes of complex curvatures if using adaptive molding techniques such as the ADAPA tools, ADAPA tools? Do you know about that?
To be fair, I don't know the answer to that question.
Okay.
Apology.
No, and a question, is there a limit as to how many times carbon fibers can be recycled?
So that is a very good question. There is actually some really nice work from the University of Bristol about that. So I think that Ian will probably talk about that later on in this workshop. So there have been studies that show that if your recycling process is optimized, you get a small reduction of properties after the first recycling cycle, and then another small reduction of properties after the second recycling cycle. Now, I think that from a conceptual point of view, it should be possible to recycle composites in several cycles, so not only 2, but more. But I think that we still need a lot of more research on that.
Okay, thank you very much. Well, thank you very much for a very interesting talk, and we'll see you again shortly for the Q&A session. I can move on now to the next speaker.
Thank you.
So we have our final speaker for this afternoon, Professor Kristina Oxman from Luleå University of Technology in Sweden. Kristina is well known in the field. She's published extensively on bio-based materials and composites. She's also an associate editor for Composites Part A, and she's going to talk to us about bio-based nanomaterials and their use in composites. So thank you very much, Kristina.
Thank you, Steve. Let's see if I can share the screen here. Okay, I think is it correct now? So thanks a lot. This is first time for me to talk in this type of web conference, so it's a little bit strange feelings. I cannot see anyone. So yeah, I'm going to talk a little bit different materials than the previous speakers. It's about bio-based nanomaterials and their use in composites. And I would like to start to show some background and how this topic have developed during the years. And it's especially cellulose-based nanomaterials which have gained a very large interest, and I'm illustrating that by showing how the number of publications have increased during the years. And as you can see here, this development have been really fantastic, and we can see more than 6,000 publications on this topic. And this research was started about 1995 in a group in Grenoble in France. And I think this group was doing excellent work because so many people have been inspired by their work from start and have started to work on these bio-based nanomaterials and especially cellulose. So for those who don't know about these nanomaterials and especially cellulose, I'm showing wood as example here. So this type of hierarchical structures are very typical for natural materials, and we can separate nanocellulose from wood and also other plants. And I guess you know that wood have this type of cellular structure, and this there is one cross section of one wood cell, which is also called wood fiber, and this wood fiber is consisting of 3 main biopolymers. They are cellulose, hemicellulose, and lignin. If we are separating those cellulose nanofibers from this cell wall, they look something like that. They are forming this type of entangled networks, and the size can vary between 5 to let's say, usually 30, 40 nanometers in width, and they are in micrometer length. And this cellulose biopolymer is semi-crystalline polymer. So if we are then further removing the unorganized part of it, we can get this crystalline cellulose, which is, you can see here, this type of needle, very extremely small needles, about 3 nanometer in diameter, and they are approximately 200 nanometer in length. That is a little bit varying from different sources, but from wood it's this type of structures. And these can be separated either chemically, mechanically, or combination of those. And it's usually actually combination. And I would also like to just highlight that these mechanical properties are increasing with decreased size. If we are taking softwood modulus, it's about 12 gigapascal and strength about 100 megapascal. And then the smallest part, these crystals, the modulus is about 140 and the strength is about 10,000 megapascal. So the properties are improving a lot. And why are then so big interest on these bio-nanomaterials? I have listed up some properties which I think are interesting, and I think these high mechanical properties are interesting. Also high surface area is interesting, and they are of course lightweight. They are biocompatible, and they are forming very strong networks due to the hydrogen bonding. And this network can be good, but it can of course be a little bit giving problems also if we want to distribute them in the polymers. But we have seen also that if they are forming this strong network in the polymer, they are actually reinforcing the polymer very much. They have also high thermal stability compared to many natural polymers, and of course they are from natural resources, and they can come from residues, and they are contributing to sustainability. And if we look, we have these two photos here, those images, and the image above is cellulose nanofibers in water suspension. They are forming this type of gels in quite low concentration. Here I think we have 2% nanofibers in it, and the picture up below is cellulose nanocrystals also in water, and they are also forming gels, but you need a little bit more crystals. So here we have 10% concentration. So I'm planning to show you some examples of our work, and I'm starting with showing one study about the isolation process of cellulose nanomaterials, and then also about processing and extrusion of nanocomposites and how the properties are improved, and also effect of orientation of these materials, and then about how resin impregnation can be improved by designed nanocellulose preforms. And the first example is about production of the cellulose nanofibers from low-cost raw material. It was an EU project called INCOM, where we studied 2 different industrial residues, carrot and beer residue, both very interesting materials. And the person who was responsible of this work is Dr. Lynn Berglund, still working in our group and responsible of this fibrillation processes. We worked with the processing upscaling and the goal was to produce nanofibers as eco-efficient as possible with lowest possible energy and cost and environmental impact. And you can see here in this image, we have this carrot residue and we have this beer residue, which is called brewery spent grain. And usually we are doing pre-treatment and bleaching, for example, removing lignin, which is holding these nanofibers, gluing them together. So we need to remove that polymer. So bleaching is done, and then we are doing grinding, and that grinding is mechanical separation. And we are doing that grinding until we have a specific type of gel, this cellulose nanofibers. And during that process, we are measuring viscosity and of course time. And in this picture, you can see this carrot fibers. We have this brewery spent grain, and then we have also kraft pulp as a reference material. That is common pulp from a paper mill. And what you can see here that this carrot material, that viscosity is increasing very fast compared to the other ones. That means that we are doing this fibrillation very efficiently. And at the same time, you can see that this brewery spent grain, it's very difficult to come up in high viscosity level. And this means that it's difficult to fibrillate that material. And we also made eco design optimization by reducing pre-treatment step. And we did that for this carrot material. And basically we reduced one step. We reduced sodium hydroxide step, which is usually used to remove some of hemicelluloses. So we didn't do that at all. We just made this bleaching, and by that we could reduce the use of chemicals and of course water. And that was shown that this reduction of this step was reducing 75% the carbon footprint and 50% of the cost. So that was very efficient way to make this process even more eco-efficient. Then the second example here is about processing and about liquid assisted extrusion of cellulose nanocomposite. And that was the EU project Eclipse, where the aim was to develop biodegradable plastic bags for protection of bananas during their growing. And the person who was in charge of that work was Dr. Natalia Herrera. Natalia is nowadays working at Imperial College in London. Basically, we wanted to develop PLA bags as PLA is biodegradable and it can be composted after the use. However, the drawback with PLA is that it's very difficult to blow mold to bags. And also, if it can be done, these bags are really brittle and difficult to use. So we wanted to make some kind of softer material, which is more reminding polyethylene, which is the bags that I use today. Here we used also cellulose nanofibers, and these nanofibers were also from residue source. They were from this banana residue, and we mixed those with the water and also with solvent and plasticizer. And this plasticizer was used to try to make the PLA softer. This suspension was fed in the extruder together with PLA, and these solvents was evaporated during the process. And we made very nice films where these nanofibers were well distributed and dispersed. And here is just some example of how this materials fractured surface are looking. And we are, if we are looking pure PLA, you can see quite brittle fracture. And then when we have added 20% plasticizer, this fracture is getting very tough. So the material is getting much more tougher. And when we are adding 1% cellulose nanofibers, again, this fracture surface is quite different, but we are still having good toughness left. And maybe you are now wondering why we are not just using this 20% plasticizer, because it's making the material more tougher. But the problem is that this plasticizer is affecting the melt properties of the polymer, and it's not possible to make blow molding of plasticized PLA. It doesn't have any melt strength. So adding 1% cellulose nanofibers actually could improve the melt strength, and it was still having a good toughness on the material, and we could make this type of bags. So we continued with the same material. We were interested to see that can we improve the mechanical properties of that plasticized composite by making solid state drawing. And as you can see in this image, we could improve the actually little bit modulus, but strength and especially this elongation to break and with the 2 and 2.5 draw ratio. And this polarized optical microscopy image here show also that we have some orientation in the structure. And when we have the more closer look on the structure, we etched out the amorphous PLA, and we can see this orientation, but we can also see that these crystals are growing perpendicular to draw direction. It's this kind of shear induced crystallization, and it's forming this cis-kebab structure. It is very interesting. So that was then leading that we were even more interested about this orientation, and if we could improve the properties of PLA with cellulose nanofibers without any plasticizer. And this work was done by Dr. Sisiukeng Edi, and this was one project financed by Wallenberg Wood Science Centre. And in this work, Edi made crafting of nanofibers with the polyethylene glycol. And we know since before that this is improving the dispersion of the nanomaterials in PLA. So our idea was that we are trying to make composite with very, very good dispersion. And she did those composite with solvent casting, and she made drawing in 100 degree, and she managed to have as high draw ratio as 8 on these materials. And you can also see here that films are transparent before and after the drawing. And if we look polarized optical microscopy images of those films, you can see the composite without this grafting deck and with, and we can see that the composite without that PEG is not so homogeneous, and we have some marks from the drawing, which is indicating that we don't have so good dispersion of the nanomaterial. And then the other one where we have this PEG grafting on the nanofiber surface is the film is much more even and homogeneous. And if we are looking the mechanical properties, you can see quite a big difference from isotropic composite film to aligned one. And you can also see here this, this is the pure PLA, which is orientated. So you can see that this is improving. And then material where we have just added nanofibers, and then this one where we have this polyethylene glycol, which is improving the dispersion. So the maximum strength is improved from 67 megapascal of the isotropic to 343 for the aligned composites. Then I have the last example here about cellulose nanofiber networks. And I told earlier that nanocellulose are forming this strong network, also we can call it nanopaper. And the properties of these networks are quite impressive. So if we are taking a look on, for example, carrot nanofiber network, we have a modulus of 12, almost 13 maybe, and strength about 250. It's a little bit better than wood-based nanofiber networks. And that the reason for that is that these carrot nanofibers have a more homogeneous fiber size. But then I found a work made by Hossein Sehagoui, and he used tempo oxidized nanofibers, and he made a cold drawing of the nanofiber network when it was wet, and he managed to get the draw ratio 1.6 and managed to get actually orientated network. And you can see that the properties are double of our carrot nanofiber when it's slightly oriented. So of course that would be really nice to use these networks in composites, and they are also work done where people have impregnated these nanopapers with resin and got very high mechanical properties. But there are some problems. This dried network from water is really dense, and you can see here is the same image of the network. We can almost not even see the fibers here, and there are no pores. So it's really difficult to get impregnated with the polymer resin, and also those work which are published on that usually that they are using solvents to reduce the viscosity of the resin, for example, or then that impregnation is done for a very long time. So our interest has been to try to find a way how these nanofibers could be used in conventional resin infusion process. And for that, I have one PhD student, Tuukka Nissilä, who have been developing cellulose nanofiber aerosols as preform for vacuum infusion. And he have made this kind of extremely light materials from nanocelluloses. They have very high porosity, 99%. Density can be only 9 kilogram per cubic meter. And they have also very anisotropic structure. And this is because ice crystals are growing through the suspension, and then this ice is sublimate, freeze-dried, and we have these channels through the structure, which are helping us to get the resin in. And here you can see computed tomography image of this kind of material. And our resin infusion setup for this nanocellulose preform. So we have the preform here before resin applied. Then after the resin is applied, of course, we are compacting the preform, and then here we are infusing it, and it's going very well. The fiber content is only 12%. And of course, we are trying to work to increase that fiber content. Here is how the composite looks like. And the properties, the resin is a bio-based epoxy, it's this super sap. And you can see that this composite have anisotropic structure, so they have higher modulus in one direction. So to conclude my talk, I have been telling about industrial side stream and that can be a sustainable source for nanomaterials production. I have also shown how the orientation of composite structure can improve the mechanical properties, and also that it's extremely important to get the nanofibers well dispersed and distributed in the polymer. And also this last example about epoxy impregnated nanofiber pre-phosphate orientated structure. And then, of course, I would like to thank you for listening, and also want to take this opportunity to thank our financiers.
Okay, thank you very much, Christina. Do you want to unshare your screen now?
Yeah.
And perhaps Soraya and Steve and Mark could put the camera on as well.
I can stop this.
I think you're fine. It's okay. It's stopped.
Stop. Was it stopped now?
Yes, it is. Yeah.
Okay.
Steve and Soraya, could you put your cameras on, because we'll go to the final Q&A. We've just got 10 minutes to do that. I have one question, particularly for Christina. There was a question about, just let me find it in the list. There was a question. Oh, that's right. Thanks for the presentation. This is from Mariana Correa. Thanks for the presentation. Is there any research in nanomaterials which are seagrass based?
Yes. I don't know what she meant with the seagrass, but we are, for example, working with seaweed.
Yeah, okay.
And there are other people also we have seen who are working with algae and that kind of thing.
I mean, I'm aware actually in the UK there's a group in Napier University who are looking at extracting cellulose from brown seaweed.
Yeah.
There's quite a big industry in Scotland for alginates, but actually there's a very high cellulose content in seaweed up there, so they're looking to extract that from there. So there's an industrial process for doing it. So yeah. Just to move on then, thank you very much, Christina. That's great. I'm going to ask questions now, sort of generally of the panel. The top question, there's a question that Steve had a go at answering, but I don't know if the other panelists want to have a go at answering this. Sorry, Mark, I think you had a go at answering this one, but maybe Steve and Christina and Sarai could have a go too. How do you measure sustainability from a life cycle standpoint? You might have the same answer. It's difficult, right?
Well, I would say you'd need to do some life cycle analysis, and I've been working with a few colleagues, and we have done quite a lot of life cycle analysis on the whole recycling of composites and applications for using the recyclates, and looking at the overall life cycle analysis. So it's life cycle analysis is the answer here, I think.
Yeah, we had yesterday we had a talk specifically on life cycle analysis, or life cycle assessment, as it probably should be called.
Yes, yes.
Now, another question here, perhaps for you, Steve, and maybe Soraya, I don't know. Has much research been conducted on recycling natural fiber composites? And is this research limited by process temperatures? That's a question from Andrew Carlin.
So I must say I've never done any work looking at the recycling of natural fiber composites, and the processes that I've described for carbon fiber wouldn't be appropriate for natural fibers, because the temperatures are high and the natural fibers would be, I would expect the natural fibers would be degraded under those conditions. I don't know if any of the other speakers would like to add anything.
I don't know if I can answer on that, but of course those natural fiber composites with thermoplastics can be easily reprocessed and used.
Yeah. Soraya, did you want to add anything to that?
I just wanted to say that there is also a question of the cost and whether the cost of the recycling process actually, so whether that will actually be worse than making new fibers.
I think this question relates to you, Soraya, your presentation, Soraya. It's from Mariana Correa again. Does the orientation of the fibers for both carbon and glass reinforced composites have any influence on the difficulty of the methods? What about the number of laminates?
So I'll try to interpret that question. So the stiffness of the fibers, it has an influence on the flow. The thickness of the laminate, it also has an influence in the flow. So the thicker the laminate, the more complex structures you get during the manufacturing process through the thickness direction. Do you think that answers the question?
It may do. I don't know. Unfortunately, we don't get any feedback. So, but anyway, I hope that answered your question, Mariana. Are you able to recycle carbon fiber products if they're coated with paint or other substances? And that's I guess.
Well, I could answer that question because we have done that. So we've done that in our fluidized bed process. We have processed end of life parts and shown that any organic material will just be oxidized away, and you can recover. And if there's any metal there, it will stay behind in the fluidized bed, and you can still recover carbon fiber. So that was one of the advantages of the fluidized bed process. It was originally developed as a robust process for end-of-life composites.
Yeah. That was a question from Natasha Rees. Fanran Meng has asked a question: how can we best estimate the cost of chemical recycling solvolysis process, considering it is an early TRL versus pyrolysis? So I guess it's to say those are very early stage, and how do we?
Yes, that's right. Yeah, so Fanran is in fact a colleague of mine at Nottingham, and I might have a word with him this one later. But I have been involved in some work where I was once involved in a European project a few years ago where we were looking at some materials at the experimental stage, and then trying to understand what the life cycle analysis will be when we scaled it up. And you've just got to take a process which might be you might be trying out at a sort of laboratory scale, and just do some theoretical analysis just to determine what would happen. How would that process be scaled up, and what would the energy and material flows be when you scaled it up? So I think that's the only way of dealing with a process that's at a very low TRL. You've just got to do some theoretical modeling of how that would be scaled up to understand what the life cycle analysis would be if it was at commercial scale.
Yeah, I'm very sorry. I think we've only got time for one more question. And I'm sorry, Mark, I think you answered all your questions already, so I haven't got any specific ones for you here, but we will send you those questions about the individual projects and products out of the meeting. It says, thanks, Christina, for your excellent presentation. Is it possible to use these cellulose nanomaterials into as super absorbent fibers? So that's a question from Dr. Jafari.
Yes, of course it is. They can be used as an absorbent.
Yeah, okay. Thank you very much. Well, thank you, everybody. And thank you also to all the presenters today. I'm just going to share my screen finally, just to make it known to you that we have a website. So there's a Sustainable Composites Future website. We are programming all week. So this was day 2 where we were looking at sustainable materials and the supply chain in composites. Tomorrow we're going to be looking at sustainable manufacturing of composites. And on Thursday, we're going to be looking at sustainable composite products. And on Friday, we would really like people to stay around for the workshop that we're holding. We do have a number of guest speakers throughout the week. On Friday, we have Nadeem Zahawi, the MP and Minister for Business and Industry, and also Jane Nicholson from EPSRC, Richard Oldfield, who's the Chief Executive of the National Composites Centre. And so it's, it's going to be a very good week for us, looking at all different aspects of sustainable composite materials. So I'd like to thank all the speakers for today and the delegates for their contributions. And I look forward to you all joining us tomorrow. It's at 2 o'clock. So thank you, everybody.